Alright, so last time we talked about covalent compounds and organic compounds, how to name them. Now we're going to talk about polyatomic ions. A polyatomic ion is an ion made of multiple atoms, and those atoms are held together by covalent bonds. Okay? That's polyatomic ion. They usually have common names, and there's nothing for it but to memorize them or look them up. So some examples: ammonium is NH4+. Remember, ammonia is NH3. Hg2, 2+, is mercury 1. So this would be mercury 2. Mercury all by itself, taking a 2+ charge, is mercury 2. When you have two mercuries bound together with a 2+ charge, each one would have a 1+ charge, so it's mercury 1. Okay. If it's O2, 2-, then it's a peroxide. Okay. And you need to be careful about peroxides because they can mess you up. And I will always strive to make it perfectly clear whether something is an oxide or a peroxide. Okay, so if you combine sodium with oxygen, you bring the charges down and you end up with Na2O, sodium oxide. But if you combine sodium with the peroxide, then you bring the charges down and you get Na2O2. Now you'll remember, excuse me, when I talked about naming ionic compounds, I said you have to reduce the ratio. Well, this is the reduced ratio because this has an invisible set of parentheses and a 1. Okay? Because that's what you do with polyatomic ions when there's more than one of the polyatomic ion. You put parentheses around it and get a number of its own. So this is 2 sodiums bound to a single peroxide. Okay. So just to give you another example, here's ammonium with oxygen. You bring the numbers down, and it's NH4 2O. And that gives you ammonium oxide. So naming things with polyatomic ions is pretty much the same as with regular ions, except that you use the name of the polyatomic ion regardless of where it occurs. So if it's a polyatomic cation, then it goes in front. If it's a polyatomic anion, then it goes in back. And either way, you would just use the name of the polyatomic anion. And so our last one is carbonate. And I can give you an example with 2 polyatomic ions. So if you have Hg2, 2+, and CO3, 2-, okay, this is mercury 1 carbonate. Okay, just the name of the polyatomic cation and the name of the polyatomic anion. Okay, and you bring the charges down, and you would get this like that. And now you do have to reduce the ratio. 2 to 2 becomes 1 to 1. It's just Hg2CO3. Okay, so that's mercury 1 carbonate. Now, polyatomic ions, you have to balance the charges just like normal, then minimize the ratio outside the parentheses, not inside the parentheses. Okay. And the normal naming convention is just replace whatever would be there with the name of the polyatomic ion. You're going to have to learn to recognize the polyatomic ions, and you're going to have to learn to be careful of peroxide and mercury 1. So for example, take a look at this guy right here. Titanium 4+ and oxygen 2-. You bring the charges down, and you get titanium 2, oxygen 4, which reduces to TiO2. and that is titanium 4 oxide. Now we take a look at this guy. Titanium 2 plus, O2, 2 minus. You bring the charges down, and you get Ti2, O2, 2, which reduces to TiO2, titanium 2 peroxide. So you'll notice that titanium 2 peroxide looks exactly the same as titanium 4 oxide. I will definitely always strive to avoid giving you anything that can do that. I may not succeed, but definitely be careful. Whenever you see O2, be alive to the possibility that it could be an oxide or a peroxide. And the same thing goes for if you ever see Hg2. Okay. The 4 minus anions are few and far between, but they do exist, so it's possible. But peroxides are more likely to trip you up. Now, the polyatomic ions you're most likely to run into are the oxoanions, or the oxyanions. That is going to be something bound with some number of oxygens. Okay? So the one we saw before was over here, was carbonate. These follow a trend, okay, where you'll have XON as whatever X is, 8. Okay, so for example, you have NO3 minus is nitrate, CO3 2 minus is carbonate, PO4 3 minus is phosphate, SO4 2 minus is sulfate, ClO3 1 minus is chlorate. Okay. So those are a bunch of oxoanions or oxyanions ending in ATE. Now, if you remove one oxygen, you have one fewer oxygen bound to the same element, then it's going to end in ITE. Okay. So NO2 minus is nitrite. CO2 2 minus would be carbonate. Sorry, Star Wars fans, it's not a preserving mineral. PO3 3 minus is phosphite. SO3 2 minus would be sulfite. And finally, ClO2 1 minus is chlorite. Notice that they all have the same charge. NO3 1 minus, NO2 1 minus, 2 minus, 2 minus, 3 minus, 3 minus, 2, 2, 1, 1. Okay. So these oxoanions, oxyanions, all have the same charge based on the element, okay, that it's bound to. Now, some of these extend beyond 8 and 8. They can have more oxygens or even fewer oxygens. Okay? And for that, you have to put a prefix on the name of the anion. So if it has even fewer oxygens, then it is hypo, whatever, ite. Hypo means less. So, for example, you can have a hypothesis, hypothesis. Hypo means weak or lesser. Thesis means statement. So a hypothesis is a weak statement. Hypothermia means that your body temperature is too low. Hypo, weak. Thermia, heat, low heat. Okay? So hypo, something that means you have even fewer oxygens. And then per, something 8, when you have an extra oxygen. Per for hyper, similar to hyperthermia, a fever. Okay? So here is an example of a full series of oxoanions, the chlorate series. So hypochlorite with 1 oxygen, chlorite with 2, chlorate with 3, perchlorate with 4. So Coming over here, nitrate and nitrite are the only two for that series. Carbonate, carbonite are the only two for that series. Phosphate, phosphite, sulfate, sulfite are the only two for those two series. But the halogens, whoa, that was... Okay, so the halogens, however, all have 4 members of their series. Not fluorine. Fluorine is the exception, but chlorine, iodine, and bromine. Those 3 all have oxoanions with 4 members in their series. So hypoiodate, so you could have hypoiodite, iodate, periodate, and similarly hypobromate, hypobromite, bromite, bromate, and perbromate. Okay. So, but other than that, it's hard to really get a good fix on the pattern. Fortunately, even though there are a lot of oxoanions all told, there aren't all that many elements that form oxoanions. So you have the 3 halogens, then these 4. Okay? So nitrogen, carbon, phosphorus, and sulfur each have 2 members in their in their series. The halogens all have 4. So maybe that'll help you to remember. And then just phosphor and sulfur, they're further down, they're big. Carbon is further to the right, so it gets more oxygens. But actually, no, that's a perfect way of recalling it. So phosphorus and sulfur down here, they get 4 oxygens. Carbon and nitrogen, they're up a row, 1 row up, 1 fewer oxygen. That might be the way to remember it. And then the halogens all the way over to the right, they get a lot of oxygens just because halogens are really electronegative. Okay, now, just as hydrogen plus a halogen can make a hydroacid, or hydrogen plus sulfur to make hydrosulfuric acid, you could have hydrogen plus an oxoanion to make an oxoacid. And this is where we're finally going to run into sulfuric acid. Because, once again, as a solid, hydrogen something 8, hydrogen something ite, or hydrogen hypoite, or hydrogen per 8, right? But when you dissolve it in water, then it becomes an acid. If it ends in ATE, then it ends in IC. So H2CO3, hydrogen carbonate, becomes carbonic acid. That's what they put in soda. But it's also what's responsible for our oceans becoming more acidic as we pump more CO2 into the air, because H2O and CO2 make carbonic acid. If it ends in ITE, then it becomes an us acid. So hydrogen chlorite, or actually hydrogen hypochlorite, becomes hypochlorous acid. It's not a perfect system. Once again, I blame the Germans. But it's what we have, and I don't think it's going anywhere. The oxoanions and the oxoacids are the ones that are here to stay forever. Because once again, we use them all the time. So H2SO4, hydrogen sulfate, becomes sulfuric acid. H2SO3, hydrogen sulfite, becomes sulfurous acid. Sulfuric acid, we use it all the time in lab. It's a strong acid. Sulfurous is a weak acid. We don't use it nearly as much. But you also have HClO. Actually, we already looked at a bit of that. So let's go with bromine. HBrO, HBrO2, HBrO3, and HBrO4. So they all start with hydrogen in their solid forms is what we're starting with. So this is hypobromite, bromite, bromate, and perbromate. This is the fraternity's oxoanion, I guess. All right, and when you dissolve them in water, you get that looks awful, but I can undo it. Hypobromous acid, bromous acid. That's 15 minutes. We're almost done. Bromic acid and perbromic acid. Okay. So that's the oxoacids. Once again, you'll see that there's the difference between the solid and the aqueous forms and so on, which is annoying, but it's one of those things you just gotta know because it's not going anywhere. All right, and we have quite a bit left over, so we will start hydrates in our next lecture.